Hi all, this is Claudio from xfem.com with the new live stream regarding and containing finite element analysis in ANSYS object. Let me firstly share my screen. And give you a very brief reminder of fracture mechanics, let's say. So, in fracture mechanics, we study how cracks propagate in materials, usually in time, usually due to fatigue load. This is the nutshell, yes? And there are mainly there are three, let's say, types of cracks or openings, and so on. You can find this. Usually, these are studied by engineering students in the second semester or the extended study of strength of materials, usually. So we have the crack, and it will go here on the left and here on the right once we pull from these sides of the specimen. There is a lot of theory, plasticity or its absence. Of course, there is plasticity because there is rupture, and it's related also to ductile or brittle materials. We have the energy developed at the base of the crack, and the main equation, let's say, is made with these stress intensity factors, let's say, usually. There is also an evaluation with J integral. You'll this one, you'll see it in ANSYS in a few minutes. So let me tell you what I'm talking about. Let me firstly, because there are standards and we should use the specimens for such tests. Let me show you how it looks like. One of these specimens. They look like this. Yes. If you cannot see it very well, this one. This is very briefly how it looks like. Yeah. It's just a kind of a plate, let's say, and it's split. We need, in ANSYS, we need to kind of develop further this notch, and I will show you in a few seconds. Look here, exactly at the. Can I zoom in? Yes, exactly here. Yeah, you can say, for example, that the notch is finished here, but no additional. It has an additional. It has a supplementary, very acute angle groove, let's say, or we call it crack initiation, yes, area. And you can see it further here, even though it's very small. This one. I'm talking about this one because you'll get to see it in a few seconds in the 3D model. For example, in one of my previous tests that I have performed these days, there is this geometry. Look here from GrabCAD, for example. And I would like to show that this geometry is not correct for smart crack propagation in ANSYS. Let me show you what I'm talking about, because there are multiple ways of cracking, of achieving and studying fracture mechanics. So once we go in model, this option of crack propagation of fracture mechanics is available only in static structure. Yes, because it's is something, let's say, not realistic. It's not mesh erosion as were used in SPC dynamics. Only it's something theoretical let's say. Yeah. I would like to show you the part with the fracture, if possible. Exactly. I cannot activate it because it's already inserted. Insert a fracture folder object. Let me see if I can show it to you in its full glory. For example, I don't think I need a geometry, but nevertheless, I will give a geometry here. I'd like to show you the tool, the option for the tool, yes? The tool is here, the fracture mechanics tab, let's say. Let me see if there is a question or something. Okay, we already have dictators, welcome. This is a very, this domain, fracture mechanics, it's pretty niche. I would know it's hidden, but it's not so very common, let's say, and studied by other people, even though it's very important usually when studying large structures. I don't know, tanks, fan blades from turbofans, bridges, whatever, metallic structures. So what I was talking about, this is the geometry that I have found on GrabCAD. Look here. If we go on GrabCAD and look for most light, I think, and search for compact test specimen. This is how the part is named. If we search for this, needle in a haystack, specimen. Yeah, so we found this part. It's not this one. Nevertheless, what I want you to see is the fact that the notch is, let's say, incomplete. With this one, we cannot propagate cracks. Let me show you. So I was talking about the option. This is the option. In order to start fracture mechanics, we click here, and it says insert a fracture folder object, different types of cracks, smart, delamination, deboning, whatever. Let's click here just for fun, because we can see what types of cracks we can have. Yes, arbitrary, semi-elliptical, elliptical, ring crack. These are kind of standard, let's say, and they do not allow a nice fracture, let's say. What we are going to use today, this one is interesting because here we can apply a surface body. Just imagine like a coin, but it should be a surface body to have a 0 millimeter thickness, and we can apply this one anywhere on the part, and in principle, this small surface that we'll apply will propagate a crack. In principle, it's not the topic for today. It will be for a later stream. What we're doing today is this one. It's called pre-mesh crack. I'm doing this one because, firstly, I have studied it along the years, and it looks very nice, and it's a good balance between theory and standard. These are standard and not very attractive models of cracks, let's say, or fracture. This is very eye-catching, and it's at least for beginners, this is very good to start, and it's very attractive. And this is being paired with this one, Smart Crack Growth. This is the so-called XFEM, the extended finite element method, which exists in other software. Also in ANSYS, XFEM exists in ANSYS, but let's say the implementation of XFEM here in ANSYS Workbench is made with custom, with a custom XFEM here in ANSYS Remeshing. And this custom XFEM is called SMART, which SMART is an abbreviation for, let's see for what. It was morphing something SMART, ANSYS SMART acronym. Yeah, separating, morphing, adaptive, and remeshing technology. Yes, this is what SMART is about. And I would like to go on YouTube and look for. These are my videos. Okay. For example, this one, yes. What you see here is an application of the. What you see here is an application of pre-meshed crack and smart crack growth, these ones. And this is what we will do today. I will use, of course, another geometry. This is the plot that we desire to have at the end. Yeah, the length, let's say, of the crack over, or plotted against the total number of cycles, dA over dN. The crack is being propagated in a certain number of cycles, because this type of crack is a result of repeated loads, yes? Let me see if my image is correct. Okay, it's correct. Fatigue, loads, machine, apparatus. Let's see if there is a machine or something. Yeah. So one part is fixed, this one, and this one is pulled. And a certain load, not very much, yeah, I don't know, 10, 100 newtons, 1 newton is being applied, is extended, yes. And of course, let's see, fatigue loads on compact test specimen. Test specimen. Yes, so here you can see how it acts. Here is the apparatus, yes. Here the crack opening, I think, is measured. Compact type specimen under test. And for example, this COD is abbreviation for crack opening displacement, I think, deflection or something. And it measures, yeah, the distance between what we call crack mouth, yes, and the mouth moon distance that appears. Here you can see that there is no crack, no real crack, let's say, because the elements remain here. But we aim to achieve proper function. For example, so today we are using pre-meshed and smart crack growth. I will show you this geometry that is not correct until we notch it even further with a very small acute angle pre-crack, let's say, or a crack initiation. And I would like you to see that it didn't work, okay? It didn't crack. Come on, do you want to show? Yes. Look here. So I have fixed here, I have pulled outwards, and there is no cracking, okay? Let me animate. There is no cracking propagated here. And this is usually, for beginners, this is usually a stopping point. So usually very few people insist and persist until we have a crack, okay? So we do have a stress intensity factor, which is not very revealing, okay? Because it does not propagate and the values are very small, okay? So for example, let me show you some typical values for do we have typical, oh yes, so some typical values for CIF, for stress intensity factor, should be around between 40 and 200 megapascals. And here we have megapascals, yes. It's very small. It's negligible. Such a value will not propagate crack, let's say. So this is something that kind of went correctly, but it didn't finish, okay? It needs an additional micro notch. If we call this a notch, it needs an additional notch. I can show it to you from an airplane view how these look like, but I will also, this is why I'm doing this live stream, I will also want to make it from scratch in order for everyone to understand how it's done. So this is, I don't know how much you can understand from here, and I will not explain it in detail at this moment in this FEA. I will instead go and explain while I'm performing the FEA. So my target for today will be this. And let me tell you that these days I kind of studied more about how to implement and how to achieve smart crack propagation in ANSYS Workbench. What I can tell from my experience, and I touched this domain, I think since 5-6 years now, since it began to be implemented. I think it's implemented in ANSYS Workbench around the year 2020. And what I observed in the last versions of ANSYS, it's pretty problematic. It's pretty problematic. So this is why I'm using version 2023. I have tried with 2024, 2025 and hit some blocking points until I solve them or someone solves those blocking points with other versions. I don't know. I would say that this implementation of fracture mechanics, it's I don't know how to say to remain diplomatic. I would say it's a little bit neglected. It is developed in the last years. I have seen some additional details here. I have seen some additional details in the last ANSYS versions. Only the solving of the simulation it gives many errors, at least in my experience. Okay, so let's cut to the chase and let's start. Do we have any question? No questions. So feel free, if someone will be live, except this person. Maybe I know who is this person. Okay. Let's delete this thing that it's not important. Here I will use this geometry. So from static structural, I will take the only the geometry, all right? Because I don't feel like doing it from scratch. It also took the material, the engineering data, yes? What is important here? Because a very important fact from the material standpoint is, the constant C. This needs to be explained, shown in the material properties. And this is applied, this is shown using what we call the Paris law, okay? Let me see if I can show it. Paris law of fatigue, okay, something like this. Yeah? Is a crack growth equation that gives the rate of growth of a crack. In principle, this is the equation, as I showed you a few minutes ago. Yeah, the rate means the crack divided with the number of cycles. This is the rate, and it equals the variation of stress intensity factor multiplied with the constant C, and M. Yeah, some material constants. Why I don't want to go in detail, let me at least show you this graph. Yeah. So here the crack begins. We do have something like an elastic regime, like an elastic a linear domain of crack propagation. Then here the crack is the propagation of crack is almost logarithmic or exponential. I don't know how to say it. Yeah, so it's sudden, it's catastrophic here. What we're interested in here, we're interested in this domain, in the linear domain. This is what we're interested in. Let's see if we have a better image. Yeah, can I zoom in? Yes, I can zoom in. This is what we study normally. We do not study the crack initiation because we have made the notched, yes? We're studying this. And when the stress intensity factor exceeds a certain limit, we cannot predict how sudden will be the catastrophic fracture, final failure, yes? We cannot predict. The distance, the number of cycles between this point and the critical point, the catastrophic point, we cannot usually evaluate it, usually. But we can kind of predict linearly what will happen in this domain, which is defined and described by the Paris-Erdogan law that you have seen, okay? So in this domain, this linear domain is defined by this equation. Why I reminded you about this equation, by the way, this is the stress intensity factor here. Yeah, this geometric value, some stress, and the square root of pi and crack dimension, let's say, yeah? This is geometric factor. So the stress intensity factor, it is by itself a stress value, let's say, yes? So it's an internal pressure, let's say. All right, so this is what I have done today, and I was struggling, I will admit that I was struggling, until I have obtained this thing, and you will see it right now. Look here. This is what I would like to implement and to make it from scratch. For example, these are deformation, some stress, some strain and stress. Imagine that the stress at the end of the cracking, the stress after being cracked, after being fractured, is pretty small because there is no more stress. Yeah, when there is a fracture, the stress is very low. The stress is very high before a fracture exists. Each fracture, each crack softens, let's say, the material. It kills its stiffness very much. The material is not robust anymore. This is why the material fails, yes? And also this is reflected in having a small value for stress. And also what we want, this value. Just imagine you have a fracture of mesh, but in static. Usually fracture is made in SPC dynamics. What I can tell is that this crack propagation, this fracture is theoretical. It's not, I would say, as realistic as it is in SPC dynamics, yes? So we have the total dimension of the crack, 23 millimeters in this case, and here the total number of cycles. This is dA. If you remember from the equation, this is dA. Let me show it to you again. This one, dA, crack length. This is dA. I would call it dA, and this is dN. Total number of cycles. And at the end, we can plot them, and we will obtain something which will be a portion of this. This is what we will obtain in the end, yes? Here we have also visual. Do we have visual? Initiation. Yeah, this is what we're studying. We're studying the stable crack growth, which is predictable and linear. Yeah, we don't go before where the crack was, let's say, provoked or created, and we don't go after the linear side because we don't know the distance until the failure. And we're going here. And staying here, we can somehow estimate, knowing the KIC for steel. Let's see if, yeah, knowing the fracture toughness for steel, we can evaluate against the values that we obtain in ANSYS, Abacus, whatever software is. Steel has fracture toughness, KIC, yes, of 50 to 240 megapascals. All right, so let's see if there is any question. There is a question. Aravind, you have. Sir, how do I analyze? So today on YouTube, you put a lot of questions, and you a chassis connected by wheel to, and I need the wheel to travel a hump profile road. It's not so easy. Let me just show you one FEA, and maybe you can take inspiration from my FEA. Car. I think this simulation that I will show you, this is closest to what you need. This one. What? Ah, yes. So remember the naming, motion simulation, and you can see the drawer and the wheel is doing something like this. It is a trial. It's not my best work of art. Remember, you should start with this one. But you need to check my FEA. Yeah, so feel free to purchase. It's or you have this one. And this one is very recent, and it's by the way, if you want inspiration, remember this live stream. I'm talking to you, Aravind. Live stream 15, you do have the explanation. And the explanation shows you this. The contact between the wheel and the road. Let's see if we have others. Yeah. Come on. So go on live stream 15 and see how I've done it. If you don't want to invest some money and purchase exactly what I have done with the car. It's let me tell you, it's not as easy. It's not as easy. I have perfected this simulation, and this is the nice version. Look here. This is what you need, but it was a lot of work, and I've seen that you're a beginner, so good luck with that. Live stream 15. Go there, look, and take your time. How I get this model file? Grab cuts. Do something, okay? Model, at least do something. Not everything for free, okay? You need to also do something. Where was I? Here. This Paris law needs to be implemented. For example, the default structure steel. This is the default structure steel. Look what it contains, the default structure steel. It shows the classical isotropic elasticity, whatever. Yes, Young's modulus Poisson ratio. A second coefficient of thermal especially, don't care. It says something about the SN curve, which is useful for a pretty easy fatigue calculation. You know, the ones in static and transient. I'm talking about these ones. The fatigue tool, yeah? So those values for SN are useful for this fatigue tool, which is pretty, I would say, easy to understand, easy to implement. Everyone and their mother and their dog, they are showing it in YouTube with, yeah, for how many cycles it resists. It's not as simple as everyone says, but what I was talking about is we need these two for that tool, for this tool, for the fatigue tool. This is why it's given by default in engineering data. But what is not given by default is the Paris law, which allows crack propagation. You cannot activate the fracture tool until you have defined Paris law in our material. The definition of Paris law is pretty straightforward. It's not here, you can see in the default, because I cannot create another default now. Look here, the material is already in my library. This book says it's already in my library. I cannot create another structure steel because I already have it. It's here. But what I have added is this one, Paris law. So on top of the default structure steel, you just go for crack growth laws, and you have the only option is Paris law, okay? And you have no idea. If you have no idea about the parameters C and M for your material, you can have, I don't know, copper, aluminum. Sir, how can I contact you? If you don't know how to contact me, then it is a big problem for you. Because anyone and everyone can contact me, and you cannot contact me. Okay. So let me show to you. Just ask. You know, go on Google and ask. Paris law parameters for steel, for example, or for aluminum. Look here, and they have typical values: 1e minus 13 and 7 range between. Okay, this one. And range between 3 and 4. So now I see that my value is not so correct. 1e minus 13 and something like this. So if you need to know only two values, this one and any value between in this range and any value in this range. Of course, these values should be given by the material supply. You now have seen an example for steel, for example, another example for aluminum. Look for aluminum. This is the M. Let's see the C. The C is much higher. Yeah, E minus 9, much higher than what we had for steel. For steel, we had minus 13, minus 12. So let's go back for steel. Yeah, 1e minus 13 and 3.3. This is what we're using. This is the first start. Having the material defined, we do have a specimen with the proper notch. Yes, this is how it looks like. Instead of this portion, which existed on GrabCAD, we added this one. Besides this portion, we added this one. Okay. So where is my? This is the simulation. I said I will do it from scratch. So, hoping that you have the geometry. We do apply the material as you have seen. You can check it here. And besides the parameters for the fatigue tool, we do not care about this one. We care about the parameters for the fracture. Paris law. These ones. Without these ones, we cannot have crack propagation. These ones, we don't care in this simulation. All right, now, be focused and pay attention. The first thing, it is preferable to do the EFA with tetrahedrons. So, change the method to tetrahedrons. At this moment, we will leave the mesh as it is, even though it might scream in other people's brains that it's too coarse. we don't care about its coarseness because the mesh will be remade, let's say. Yes, the crack remakes, adapts the mesh as it goes. You'll see in a few minutes. So, as I promised, we're on model, fracture. We're using pre-mesh crack. And it requires for crack front and crack faces, nodes, and whatever. I made this on because we will need the crack front, the top and the bottom. You will understand in a few seconds what I'm talking about. Look here. We will define a coordinate system here. Let's see. Coordinate system, click. Now we have many options to define this coordinate system. Just for fun, let's select this crack front, this edge. For fun, we can select other faces. What you need to consider, always the direction of the crack propagation should be x-axis, along the x-axis. Remember this. Or somewhere along, all right? But we should not have other axes. The y, the top y, is called bottom, and down, the negative orientation is called, so the top is called top, and the positive is called top, and the negative is called bottom of the crack. So the crack is defined by the front. This is the front, this edge is the front of the crack. This surface is the top of the crack, positive y, and this surface is the bottom of the crack. This is what you need to know regarding the creation of the crack. How do we do this? Look here. So, select the edge. This is the edge. We need to create a named selection. We will not go with right-click, create named. Only what I'm doing, it's just pressing the letter N. N from the keyboard, it's so easy. Yes? So this is what I'm doing, N. I will give it a name. I said this is the front. And it created here, this name selection, yes? This is the front. We changed the filter, the geometry filter to face. N, create name selection, N, top. We repeat, click this face, N, or create name selection, and I abbreviated to bot from bottom, okay? This is what we need, front, top, bottom. Now, if we have a mesh generated, as we have here, we can right-click and scope only the nodes of these selections. Create nodal named selection. Automatically converts the geometry into nodes. This is what we need. Let's do this. Create nodal name selection for all three. And let's remember what we were talking about. Yes, rename, top, front, top, and bottom. All right, why are they useful? At this moment, I can delete that, but I think maybe they will be needed later when I'm regenerating the mesh. So we will leave everything like this, even though the names are being repeated. It's not, we don't care. At this moment, we don't care. What we care is here to assign these. Crack front. Until we find the front, top, and bottom. Crack front, top face, bottom face. Now the crack looks like here. Look. What I have forgot is, instead of global coordinate system, which assigns here, and it's not correct, we'll not have cracking here. So if we forget this here and we don't choose the proper coordinate system, there will be no crack propagation. Instead, we choose here, this one. You remember? We have done this a few minutes ago. This is why it's called top. Yeah, it shows the direction of the top. The opposite one is called bottom, and the crack front is on the x-axis, is normal to the x-axis. We can rotate this in order to have this semicircle, half coin, whatever. We can have it buried inside the material. It's not important. This semicircle or semi-disc, whatever, it shows the plane of the crack. We don't need more than this. And it's only the top of the crack is shown, okay? Let's see. So what we need more? We have found out how to create the crack. And now let's do or click here or wherever, smart crack graph, okay? It asks for the pre-mesh crack, just double click, pre-mesh crack, and it's done. We do have the material defined. And let's see if it goes with life cycle prediction. I couldn't do it with life cycle prediction, but there is also this option, cycle by cycle, and the default is 10. Let's leave this default. If it doesn't work, we will do it with cycle by cycle. Now, let's apply the loads. We do have a fixed region and a force. We will make it on the positive y-axis and make it maybe 1 Newton. You need to understand that what we do here is ad hoc. This geometry, I cut this geometry from what existed on GrabCAD. On GrabCAD was a lot chunkier, was a lot. Do I see here GrabCAD? No. It was much more robust. So I'm assigning some arbitrary values, let's say. I hope you can see the. Can you see the values? Not these ones, but these ones. Do you see? Yeah, you can see the values. So what I'm telling you is you need to tailor the force according to the geometry that you have. So where you need to work is with the mesh, leave the mesh default. Don't go for refinement too soon. And we need to work with this force value, because this force value, this magnitude, it's a make or break for this FA. So let's go here. It always shows a question mark because it does not accept to find out the J integral together with the stress intensity factor. You need to choose one of these. This is why we make this one now. You see the question mark disappeared. We leave everything like it is. It's not a large deflection simulation. You'll see the displacements, the total deformation in the end. Let me show it to you here. You see, yeah, it's very small. And the software auto scales to show you this but in reality, the crack opening is very small in reality. This is why we are still in the strength of materials domain. We are in the microscopical small deflection and the small deformation theory of strength of materials. Yes, we're not in nonlinear side. We're not in nonlinear kinematics, whatever. No, we're not there. We're in static structure with the small deformation. So at this moment we can ask for these values, and let's see if we have a crack propagation. Yes, I have struggled today a few hours until I achieved some crack, and no, so please have patience. The FEA worked, only there is no crack propagation. I would like to. This is how it looks like when there is a crack propagation. Unfortunately, the computed number of cycles is less than 1. What this says, in my opinion, is that the force value is too high. Is so high, let's say, that it goes towards what we call the static crack growth. Look here, static. If we have a too high force value, but because we want to stay in fatigue, we'll keep it like this, yeah. And this is why what we need to do is to decrease the force load. This is my assumption at this moment. So, for example, let's make this 0.1. This is what I wanted to apply here, fracture tool. In the fracture tool, we select our crack, which is called Remesh crack. And besides the stress intensity factor, we are going to ask, of course, we cannot ask for J integral, but we can ask for crack extension length, crack dimension, let's say, and for the total number of cycles. This is, as I told you, dA, and this is dN. I have changed the material parameters for the Paris law. I have changed the C. For example, in this simulation, I had the coefficient C 1e minus 11, you see? And I had achieved this cracking after many trials. And here I have changed the FEA totally by assigning 1e minus 13, which I would say is more realistic for steel. But I have changed the entire approach of this simulation, let's say. I would opt at this moment to stay with 1e minus 13 because we know exactly what we need for structural steel. Instead, here, we're going to change from life cycle prediction to cycle by cycle. We keep the default 10. Save. And solve. Let's see if I can increase this. Yeah, no crack. And all right, let's refine a little. Resolution 4. And let's solve it again. No, and here, let's increase this, I don't know, maybe to 1000, incremental number of cycles. Yeah, so no crack propagation. It seems that the load is too high. Can I decrease the load 0.05, for example? Come on. What should I do? What I was also doing in the past, here I was changing to off and 10 substeps. Let's see if it works. Even though normally nothing is changed. But I'm showing you all the options. Oh yes. So this was, yeah, small trick. And the crack now propagates and it fractures the material. It ended in an error, and it's normal to end in an error. You will see why. Let's firstly investigate here how it looks like. This is how it looks like. Yes, it started, first step, and you can see the first increment of fracturing, then the second increment. So when we have these, when we have a non-zero value, when we have whatever value here, then we have crack propagation. And it says, this is crack initiation, I think, C int, calculation for crack, whatever, number of contours, and it went for maybe for five steps. Look here. Why did it stop? Look here, this is why we don't need a very fine mesh. The mesh is being remade here. The FE stopped because the crack reached the end. This is why the FE stopped. Yes, let's plot a little in millimeters. This is total fringe of the part, but the exact length travel of the crack is given by this one. Yeah, and the length, maximum length is, let's say, 22 millimeters. Yes, and you can measure it from here to here. You can see on this ruler around 22. So this is not so relevant, only it helps in animating the results. We do note here an auto scale because we're in the small deformation theory, where still in strength of materials, we're not in kinematics. Yes? We do have some very small values for strain because the crack exists, all right? The material is not heavily loaded. it's relieved of stress because there is the crack appeared, okay? What we're interested in this simulation, 1 second, let me turn off one alarm. I will get out for 1 second. Okay. What we're interested in, we're in fracture mechanics. This is what we're interested in. The value is pretty small, I would say. Let's change a little the units. And let's ask AI, let's ask AI if this value is pertinent for a fracture mechanics simulation. Do we have other questions now? I have obtained in FEA 300. Yes, this is the value. Let's close the FEA that we had in the past. And we're focusing Pascal or multiplied with square meters. Pascal multiplied with square meters. Attention, yes, Pascal multiplied with square meter. Obtained the FEA. Is it useful compared to how do we call it? Crack loss. Yeah. To the allowable, that's fracture toughness, to the fracture toughness allowable force. And said, yes, your FE output is a valid stress intensity factor, but to compare it to allowable fracture toughness, we must first convert the units to megapascal. And it's equal to 0.0032. Yeah? If we convert to megapascals, then we do have something like this. 0.1. We're there. The value is exceptionally low. For context, we should be around 50 to 100 megapascals. What do we do from here? We can see, yeah, someone from outside can say, hey, come on, what are you doing? That is too small stress, too small strain. What are you doing here? What we need to do is to gradually increase the force. For example, for this minuscule force, let's look at the total number of cycles. Yeah, so the total number of cycles is 600. In reality, we should have some millions here. In reality, yes. So my advice when starting this type of simulation, have the proper geometry, not something that I second guessed from somewhere. Let's see if I have some dimensions in millimeters. Yes, 40 millimeters. It's very small. So if we second guess ourselves and we keep coming up with unrealistic values, then of course we do not have also a realistic output. Okay. The purpose of this live stream was to initiate you in the application of the smart crack graph. I have done this. I have also led you to obtain the crack. And what I will show to you is also how to make this plot, dA over dN, yes? In order to describe the linear portion of the, yeah, this one, the linear portion for fracture, let's say. So what do we do now? We can, let me save it and then duplicate it, yes? I will write here stream 27 and I will duplicate it because I would like to test with other force values. Do I have something from the density? No, okay. The larger density of one person. Thank you for your attendance. Double click. We will play a little with some values. Let me see on YouTube if there is someone also doing this type of ANSYS smart crack graph. Let's see, yeah. Let's see. ANSYS smart crack graph. Oh, we have lots of people. This is not smart crack. This is a PDF. Compact tension. Oh, yes, this is smart crack. I remember this being my animation, my FA. This is maybe from ANSYS, yes, this is the lamination. And, oh no, it's not taken from me, it's taken from Singularity Engineering. Yeah, and also my simulations. Where was I? Here, I would like to increase the value. Let's see, 1. Can we ask, I shouldn't have done this. Can we ask typical fatigue load for steel? I would like the force, not the... So, for example, 1 million or 10 million cycles, yes? Fatigue force when testing steel. No, it doesn't tell. The force is calculated directly using the where P is the applied force and targeted cyclic stress. the dynamic section area of the specimen. So let's tell it. Cross section area of the. Let's see how much the cross section. So we need to perforate something like 20 over 5. 20 multiplied with 5 is 100. Let's say 100 square millimeters. 300 MPa let's say 100 square millimeters. High cycle for high cycle fatigue. High cycle fatigue. Remember to always ask AI because it's very convenient. The typical peak fatigue force for testing this steel sample ranges from these calculations to high cycle fatigue test target. Just apply. Calculate the low stress boundary. The typical maximum fatigue testing force for steel spans from. Oh my god. Oh my god. Ooh. Maybe something is wrong with my judgment here. Let's see if we have crack propagation for this value. No. So for 1 Newton, we do not have crack propagation. Do we have for 0.25? It's a problem with the units. I forgot to revert to meters and kilograms. It seems like it's propagating crack because it doesn't jump from 0 to 100, so it cycles through all the steps. Look here. Yeah, crack, crack, crack. Yeah. So we do have some crack propagation. I still don't like the so small values. It's a little better. Finally the SIF increased 16,000. It's a little better, and the total number of cycles 3 cycles. Only 3 cycles to break this. Oh my god. Let's verify these 16,000. And now it will say that is better. Your FEA 60 megapascals when compared to the typical allowable fracture toughness. It's in the range, is critically low, indicating potential risk of brittle fracture if these are the actual operating stresses. Yeah, so my crack is currently stable. Only the problem is that the SIF is still too low, and the material that I have, they say that it's brittle. Okay. What map did you use? All right. So at this moment, let's leave it like this. It's a blank, and let's see firstly if We have any message? No. And let's see what other colleagues of ours did. He's going through the help, yes. Semi-elliptical, we do not care. We care about the smart. There is no smart crack growth. What? No smart crack growth? Maybe here. I like the value better, is 7, and we have 16, yeah. I like this plot for the crack, for the sieve. Let's see if there will be a crack propagation. You see the very small deformation layers. Crack extension. It's not doing fatigue. The starting and stress intensity or whatever you see here is not fatigue. I'm curious if someone on YouTube shows fatigue, because this is a different dish to eat. And yeah, I don't see fatigue. It's easy to do fatigue. I don't know if he has done it. I don't know. Let's see if someone has. Yes. Does he or he? Oh, Mr. Musk from Middle East. Let's see if they know how to apply the Paris law. Do they know? Maybe they found out. It looks correct. Static again. So nobody went for fatigue. ANSYS smart crack growth. Yes, but we don't know what's inside. Other Turkish experts. Finish crack. What is this? No. We have smart crack. Static. So this is what you have learned in this live stream. Yes, doing static it's not a big deal. Believe me, I can even show you static. Yes, I can even show you. But until now I didn't see fatigue. This is fatigue. Yeah, I will show you how static looks like, in my opinion. Yeah, we can say that nobody has done. Let's see if these people, they're experts. Let's see if they have done static. I'm curious. If even they didn't do fatigue, then who is going to do it? Static. So, yeah, I rest my case, yes. I will show to you an example with static. But what? I don't have cracking? Let's see, maybe there is cracking. So go on YouTube and see how static is made. It's not very hard or challenging? Yes, we do have. Let me write here results, no? Results. Because this is nice, nicely done. Look here. But this is made static, and I would like to point you here. Static stress intensity factor and whatever, we give a value here. And I have this one. What we cannot find here, because it is static and not due to cycle loading, to fatigue, we cannot have this one, total number of cycles, because it's only one load. For example, our force for this is 250 newtons. For this geometry, look how small the geometry is. We have like a plate, 4 millimeter plate, yes, and it's 20 millimeter high or something, yes, so it's pretty small. We cannot have cycles. This thing that you see here exists on YouTube. You can see it, but what other people will not show to you is this one. And they will not show to you this one. Yes? Because I don't like the number of cycles, I will plot this dA over dN. I will plot it with my previous simulation, from my previous simulation. And my previous simulation was this one, I think. Because here I remember I had 611 cycles, if I remember correctly. Let's see. Any question from the audience? From the large audience? No question from the large audience of 0. No question. Where was I? Here. So we have, I need a number bigger than 3, okay? So let's do the plot. We're selecting both with Control pressed. We have chart. And let's plot them. We don't need time. What we need on the x-axis, let's say this is the horizontal is the x-axis. We need to have dn, plot style, whatever, linear grid lines, x-axis. I will say dn, and the vertical one will be dA. Content, chart and tabular data. Time, or we don't want time. Yes? So this is the plot. dA over dA. And let me, in order to be consistent with the units, we have this crack propagates and enlarges until it gets 22 millimeters long, let's say, in 611 cycles. dA over dN, this is the plot. Made with fatigue, okay? So from now on, due to my live stream, I expect in the next months or years, also for other people to publish fracture mechanics with fatigue and not only choosing static. So remember to also look at my other simulations. ANSYS Smart, my other simulations with cracks are these ones. This one, these ones, 2 cracks at the same time. These ones, 2 cracks at the same time. This one is made with static. 7 years ago, it was my beginning. Oh, nice. And of course, I can bet that it's made with static and not fatigue. Where was I here? Please remember to look on this FEA and see other values, other scenarios. What is this? This is one fixed end. It's not so nice. This is nice. This is what I wanted you to see. And in papers, this is how the tooth dislocates. This is how the tooth is fractured according to a load, a lateral load on the tooth. So here we have 2 cracks, one here and one here. I think this is static, I think. Yeah, it is static because we have a very high CF. Yeah, it should be maximum 200, and we have almost 2000. So I bet it's static, but it looks so nice. So nice. Yeah, after a few years since they implemented in 20, so maybe they implemented this tool in 2018 maybe, and in 2020 they allowed to have corner cracks. In the beginning it wasn't possible, but now it is possible to have corner cracks, which is pretty complex, let's say, mathematically. This is 1 or 2. Yes, we have 2 in parallel, and you can see both of them. You see the automatic meshing here, how it's refining, let's say. And this one, which is, I think it's my first. Yeah, 2018. It's my first fracture mechanics, I think. Yes. Yes, this was the beginning of the implementation of a smart crack propagation in ANSYS workbench. It's very, 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 very nice. So, ladies and gentlemen, this is what you got from me today. It's the path towards investigating the fatigue loads and obtaining crack propagation in such scenarios, not only with static forces, also everything in static structure. So this is all from my side, and if there are no other questions now, I will leave you here. Thank you for your attention, and bye-bye.